Today, we are going to look under the hood of modern artificial intelligence and talk about the engine that makes it run, which is vectors and matrices. Deep learning models may look mysterious, but underneath, they are just doing a lot of organized number crunching. In this session, we will focus on three key ideas: what vectors are, how matrices are shaped, and how matrix multiplication actually works. Once you understand these pieces, the math behind neural networks will feel much less intimidating. Think of this as learning the basic grammar of the language that AI speaks. Here is our roadmap for this mini course. First, we will meet vectors, the basic one-dimensional building blocks that store lists of numbers. Then we will move to matrices, which are just grids of numbers, or stacked vectors, arranged in rows and columns. Next, we will connect this math to real deep learning models by talking about something called D-model. That is the number of features in each word's representation, or how rich each word's description is. After that, we will dive into matrix multiplication, the core operation that lets neural networks transform data step by step. And finally, we will see how transposition, which is flipping rows and columns, helps us fix shape mismatches so our multiplications actually work. By the end, you will be able to read these diagrams and equations like an engineer, not just a spectator. A vector is simply a one-dimensional list of numbers. You can picture it as a row, for example, the numbers 1, 2, and 3 written across on a single line, or you can picture it as a column, with 1 on top, then 2 below it, then 3. The orientation really matters. In linear algebra and in deep learning libraries like NumPy and PyTorch, a vector is usually treated as a column by default. If you try to multiply two vertical vectors directly using standard matrix multiplication rules, the shapes do not line up, and the operation fails. Most of the time, we multiply a row vector by a column vector instead. That row by column pattern is the core idea that everything else builds on. Now let us see what happens when we actually multiply a row vector by a column vector. Imagine a row with the numbers 1, 2, and 3. Imagine a column with the numbers 4, 5, and 6. To compute the result, we pair each position first number times first number, second times second, third times third. That gives us 1 times 4, 2 times 5, and 3 times 6. Then we add them all together. 4 plus 10 plus 18, which equals 32. This single number, 32, is called a dot product. It is a special kind of multiplication between two vectors that always produces one number as the output. Under the hood, neural networks do this kind of dot product over and over again, just with much longer vectors. A matrix is simply a two-dimensional grid of numbers. You can think of it as several row vectors stacked on top of each other. To describe a matrix, we always say rows by columns. For example, if a matrix has 3 rows and 2 columns, we say it is a 3 by 2 matrix. In code, especially with NumPy, we talk about the matrix shape instead. The shape would be 3, 2, which means exactly the same thing, 3 rows, 2 columns. One common trap is a so-called rank 1 array, which has a shape that only says 3. It is not clearly a row or a column. For deep learning work, we prefer our data to be true two-dimensional matrices, so shapes like 3 by 1 or 1 by 3 are much safer. Now let us connect this math to AI and language models. In transformer models, each word in a sentence is turned into a vector of numbers. The length of that vector is called D-model. It measures how rich or detailed the description of each word is. Imagine the sentence, I play guitar. That is 3 words, so we have 3 rows. If each word is represented by 4 numbers, then D model is 4, and our matrix has shape 3 by 4. Rows represent the sequence length, meaning how many words we have. Columns represent the features per word, which is D model. Bigger values of D model mean more expressive models, but they also mean bigger matrices and more expensive matrix multiplications. When we multiply two matrices, not every pair is allowed. There is a golden rule. The inner dimensions must match. Suppose we have a matrix of shape 3 by 2, and we want to multiply it by another matrix. The second matrix must have 2 rows for the multiplication to be valid. Maybe it has shape 2 by 4. The inner numbers, the 2 and the 2, match, so we are good. The result will have the outer dimensions, which are 3 by 4. If instead we try to multiply a 3 by 2 matrix by another 3 by 2 matrix, the inner numbers are 2 and 3. They do not match, so the multiplication is invalid and would cause a shape mismatch error in code. Always check those inner numbers first, like puzzle pieces that need to lock together. Let us zoom in on what is actually happening when two matrices multiply. On the left, we have a 2 by 2 matrix with the numbers 1, 2, 3, and 4. On the right, we have another 2 by 2 matrix with the numbers 5, 6, 7, and 8. The result is also a 2 by 2 matrix, but each entry is a dot product of one row with one column. The top left value comes from the row with numbers 1 and 2 and the column with numbers 5 and 7. We multiply 1 by 5 and 2 by 7, and then we add the results. So we do 1 times 5 plus 2 times 7, which equals 19. The top right value comes from the same row, the row with 1 and 2, but now with the column that has 6 and 8, we do 1 times 6 plus 2 times 8, which equals 22. The bottom left value uses the row with 3 and 4 and the column with 5 and 7. 3 times 5 plus 4 times 7 gives 43. The bottom right value uses the row with 3 and 4 and the column with 6 and 8. 3 times 6 plus 4 times 8 gives 50. Put together, the result matrix has two rows and two columns, with the numbers 19 and 22 in the first row and 43 and 50 in the second row. So, matrix multiplication is really just dot products repeated for every row and column pair. With ordinary numbers, 2 times 3 is the same as 3 times 2, but with matrices, order matters a lot. Using the same two matrices as before, multiplying A times B gives us one result. If we flip the order and compute B times A, we get a completely different matrix. Sometimes the reverse multiplication is not even allowed at all because the inner dimensions do not match in that direction. This is why we write matrix equations very carefully in deep learning. Changing the order of multiplication can completely change the meaning of a layer or break the model altogether. When you see something like x times w transpose, that order is not optional. It is part of what the model is doing. What do we do when dimensions do not align, but we know the data itself is correct? That is where transposition comes in. Transposing a matrix means flipping it over its main diagonal. In other words, rows become columns and columns become rows. A matrix that was 3 by 2 becomes 2 by 3 after transposition. In math notation, we write this with a little letter t as an A transpose. In code, especially NumPy, we often call it A.t. This simple flip often turns an impossible multiplication into a valid one, without changing the numbers themselves, only their orientation. When shapes do not match, we still need a strategy for deciding which matrix to transpose. This slide shows a two-step process. Step 1 is the puzzle piece check. We look at the inner dimensions and ask, can I transpose one of these matrices so the inner numbers match? If transposing matrix A fixes the mismatch, that is one option. If transposing matrix B would also fix it, we keep both options open. Step 2 is the target shape check. Now we think about what shape we want for the result. Different choices of which matrix to transpose give different outer dimensions. We pick the option that not only makes the multiplication possible, but also gives the output shape that matches our goal. Now it is your turn to apply these rules. The first scenario on this slide is a plain dimension check. You are given a matrix A with shape 3 by 5 and a matrix B with shape 5 by 2. The question is, can we multiply A by B in that order? And if so, what is the shape of the result? The second scenario is a target shape problem. You have an input matrix X of shape 100 by 10 and a weight matrix W of shape 5 by 10. You want your final output to have shape 100 by 5. The challenge is to write the correct multiplication equation that produces that shape, possibly using a transpose. These exercises force you to think about inner and outer dimensions, not just the raw numbers in the tables. This slide walks through the reasoning for the previous problems. For the first scenario, the inner dimensions are both 5, so the multiplication a times b is valid. The result takes the outer dimensions, giving a matrix of shape 3 by 2. For the second scenario, we want an output of 100 by 5. X already has 100 rows and 10 columns. W has shape 5 by 10, which does not line up with X in that order. By transposing W, we turn it into a matrix with 10 rows and 5 columns. Now the inner dimensions, the two tens, match, and X times W transpose has the desired shape of 100 by 5. This is exactly the kind of reasoning you will use when wiring together layers in a neural network. Here we summarize the key rules you should carry with you. First, in deep learning, we normally treat vectors as columns by default. Second, matrix shape is always described as rows by columns. Remember the letters R and C, in that order. Third, for matrix multiplication, the inner dimensions must match, or the operation is invalid. Fourth, the shape of the result is determined by the outer dimensions. And finally, we can use transpose to flip rows and columns whenever we need to fix alignment or adjust the output shape. If you keep these 5 ideas in your mental toolkit, most shape errors will become easy to diagnose. We end with a reminder that understanding the rules is great, but fluency comes from practice. The best way to internalize the row by column pattern is to work through problems on paper or in a notebook. Do plenty of small matrix multiplications, check inner and outer dimensions, and practice deciding when to transpose. Over time, this will feel as natural as basic arithmetic. Once you are comfortable with vectors, shapes, and matrix multiplication, you have learned the foundational grammar for the language of AI. Everything from attention mechanisms to entire transformer blocks is built out of these same pieces.